So yeah, I'll be presenting our work TLBDR, which is about reverse engineering TLBs, translation Lookaside buffers from software. So we'll be discussing a novel way to reverse engineer TLBs, and I'll discuss the results that we obtained on Intel TLBs, which includes previously undocumented properties. And we'll discuss how you can use this knowledge to improve attacks that rely on TLB interaction. So as probably everyone knows, CPUs support virtual memory, so whenever a virtual address is encountered, we have to perform a translation to physical memory. And this is called a page walk, and the page walk involves multiple accesses to main memory because these page tables are multi-leveled. And because this is a slow process, CPUs embody a cache called a translation Lookaside buffer, or TLB, that caches recently completed translation, so that on subsequent accesses to the same virtual address, we do not require an additional page walk. So on Intel, the TLB has the following topology. We have a dedicated DTLB for data loads and an ITLB for instruction fetches. And only if there's no translation available in the level 1 TLB will the CPU consult the level 2 STLB, which is unified between data loads and instruction fetches. When there's no translation available in the STLB, then a page walk will be necessary. So TLBs are typically set associative structures, so that a virtual address deterministically maps to one of those sets, and within a set, there are a number of ways, and a translation can occupy any of those ways. Although the TLB is very good for performance, it can also be used in a malicious way. And that is because the TLB is a shared hardware structure between processes that run on the same CPU core, for example, sibling hyperthreads. So if a process makes secret-dependent accesses, then the TLB state could become dependent on that secret. And because the TLB state can be sampled by another process, by timing the access, right? A TLB hit will be faster than a page walk. This secret can be inferred by another process. So previous work, TLBleed, showed that it's possible to leak a cryptographic key over the DTLB. And although this work by Grass et al. Reverse engineered some Intel TLB properties, there were still some properties that remained unknown. And that's what we looked at in this paper. And to reverse engineer TLBs, we used TLB desynchronization. And this relies on the property that TLBs are non-coherent, meaning that whenever the page tables are changed, so a mapping from a virtual address to a physical address, then the TLB requires explicit invalidation. And if the kernel fails to do so, then we could read or execute from a wrong physical address because a still translation is used. So here you can see how that looks. We have a virtual address A that is mapped to physical address X1. If we read or execute from A, then the TLB will cache this translation so that on subsequent accesses we have a TLB hit. But if we directly afterwards change the page table mappings so that A now maps to X2, then we get a desynchronized situation where the TLB and the page tables in memory do not agree. So this is normally a bug, right? But if we can purposely create this situation and make sure that these two physical addresses, X1 and X2, contain easily distinguishable contents, 123 and 321. And now, if we read from virtual address A, we can easily distinguish between TLB hits and TLB misses. Because as long as we read 123, we know that we read from physical address X1, and thus that the TLB translation has been used. And as soon as we read 321, we know that we had a page walk, and thus that the TLB evicted our translation. So using TLB desynchronization, we can reliably distinguish TLB hits from TLB misses. And we use this primitive to reverse engineer TLB properties. So we looked at quite many properties, including inclusion policies, which decide where entries or translations reside in the TLB, may reside. Insertion policies, how are translations inserted and when. How big are the sets in the TLBs, and how does a virtual address get mapped to a set, the so-called hash function. And replacement policies. So due to time limitations, I'll discuss the replacement policies result, but the others are no less important. So we need the replacement policy because when we insert a new translation, the TLB set is likely already full, and so we need to decide which entry we evict to make room for the new translation, the so-called victim. With TLB desynchronization, we found that there are 3 replacement policies active on Intel TLBs. We found LRU, we found 3P-LRU, and the policy that we named MRU plus 1 modulo 3P-LRU4. I'll refer to it as MRU plus 1 from now. So LRU stands for least recently used, very intuitive, right? We evict the least recently used entry in the set, and we found this to be active on Ivy Bridge's ITLB. But the policy that was much more common on Intel TLBs is 3-pseudo-LRU or 3P-LRU, which is an approximation of LRU. And it approximates LRU with a binary tree, you can see it on the right, where we just have to follow the arrows to decide which of the entries needs to get evicted. So if we want to insert a new entry, say 4, we follow the arrows and override 1 in this case. And after that, we flip the arrows to make 4 the most important, most recently used entry in the set. And if we now consequently have a hit on 0, then we also flip the arrows to make it the most recently used entry. So we found this policy to be active on all the DTLBs that we considered and on the STLB of older Intel microarchitectures. But on the STLB of newer Intel microarchitectures, we found a novel policy, MRU plus 1. So this is a 12-way set associative TLB. And we found that the replacement policy intuitively divides these 12 entries into 3 groups, group 0, group 1, group 2. And within each of these groups, we have 3P-LRU that keeps track of the replacement state. And additionally, we have a root node that decides which of these groups is the victim group and which of these groups will choose the victim. And it does this by remembering the most recently used group, MRU group, and it adds 1 to that. So if group 1 here is most recently used, we'll choose the victim in group 2. So if we have a hit on entry 1, within group 0, which is where entry 1 resides, we flip the arrows to make it the most recently used entry in group 0. And the root node will remember that group 0 is the most recently used group, and it will change the victim group to group 1. And if we now want to insert a new entry, let's say 12, we override 2 and do the same. Flip the arrows and update the most recently used group at the top. So why do we care about this, apart from that it's interesting? Well, TLB-based attacks often need to evict one particular entry out of a set. For example, in the case of TLB, in order to sample the TLB state, we required to evict the entry of the process we spy on. So the naive way to do this, and this is what previous work has done, is to just override the entire set, all the entries in the set. But now that we have the knowledge of replacement policies, we can create optimized eviction patterns that evict entries in the most optimal way. So for example, if we have a entry T that gets inserted, we have the following state, and now we want to evict T in the with the least minimal steps possible. So how we do this is we issue a hit on 6 to update this lower node to point at T. Then we issue a hit on entry 2 to update the middle node to point to the right, and then we issue a hit on entry 1 to make T the next victim. So now if we issue or trigger a TLB miss, T will be the victim and we evicted it. So with only 3 hits and 1 miss, we can now evict an entry out of the TLB compared to 12 misses that were required with the naive eviction sets. So the original TLB attacks leaks over the DTLB, and we measured that using our optimized eviction sets, we can sample the DTLB 20% faster compared to naive eviction sets. But we also make it practical to leak over the level 2 shared STLB, because our optimized eviction sets result in twice as fast sampling, which brings the sampling rate close to the sampling rate obtained on the level 1 DTLB with naive eviction sets. And we introduce a variant that leaks from the DTLB and the STLB simultaneously, yielding a 5 times faster sampling rate, or higher sampling rate compared to naive eviction sets. But there are also other attacks that indirectly rely on interaction with the TLB. So we have PT hammer and ASLR on the line that rely on side effects of the page walk to hammer DRAM and break ASLR respectively. And we measured how much more efficient we can make these attacks when we use optimized eviction sets. So in the case of PT hammer, we found we have a 12% shorter hammer time, and in ASLR on the line, we found that we can break ASLR with 20% less time compared to naive eviction sets. So there were more interesting results, such as an undocumented cache that keeps track of address spaces, but I could not discuss this because of time limitations, but please take a look at the paper. So as a summary, we reverse engineered TLBs, which led us to have a better understanding of TLB behavior, and this allows us to speed up TLB eviction, improving several TLB-based attacks such as TLB, PT hammer, and ASLR on the line. Thank you very much.